Okay, so we're going to take a look at a couple of problems here. These are from the end of our textbook, the additional exercises, I believe. So the first one is prove that any graph, not necessarily a tree, with V vertices and E edges, that satisfies the inequality V greater than E plus 1 will not be connected. Okay, okay, so at first here we got to decipher first what all it's asking us here. So again, I'm going to start with letting G be a finite graph with V vertices and we'll call it E sub G edges. Okay, so I'm going to approach this by proving the contrapositive, which we know is logically equivalent to our statement. So we'll say that if, so negating the conclusion, so not connected, let's say if G is connected, then, right, I negate the hypothesis, then V must be less than or equal to E sub G plus 1, right? And in other words, E sub G must be greater than or equal to V minus 1 by rearranging the inequality. Okay. So let's start here with our proof. All right. So our proof, we had G is connected, right, by assumption. That means that a spanning tree exists. We'll call it T. Okay, and again, that was from one of the properties that we went over in a previous video. Okay, well, the tree T must have E sub T must be equal to V minus 1 edges. All right, again, also one of the properties we went over in this module here. So E of T must equal to V minus 1 edges. Well, since we removed edges, right, possibly, right, from G to create a spanning tree, then we have E of G, that is essentially our lower bound, V minus 1, right? It has to be greater than or equal to V minus 1, right? If we didn't need to remove any to have a spanning tree, if it was already a tree, well, then we have equality, right? But if we did have to remove them, then there'd be more edges in G. And that proves our contrapositive, which means that proves our initial statement, because that would always be true. All right. If V is greater than E plus 1, or the edges are less than V minus 1, then it will not be connected, right? Which makes sense, right? I get what this theorem is kind of getting at is that we need at least V minus 1 edges to connect all of my vertices, right? That is not satisfied, we will not have a connected graph, right? That's what that's saying. And intuitively, that makes sense with our examples, right? But again, those are just examples, right? If we think of, we have two nodes, two vertices in the graph, one edge, right? We think of, we add one more, right? The minimum we need to connect it is one edge, Right? So we at least need that to be v minus 1. All right, let's take a look at another example here. So here, this example, again, same from our textbook here. If a graph G with V vertices and E edges is connected and has V less than E plus 1, must it contain a cycle? Okay, all right. So here, let's write it as an implication here. Okay, so let's say that if G is connected and V is less than E plus 1, or another way to think of this, that E is greater than or equal to V. All right, again, these values of V and E are, call it E sub G to avoid confusion, the edges in graph G, right? And again, discrete values, right? So V less than E plus 1 is the same as V less than or equal to E. Okay, all right. So if this is true, right, our hypothesis, then the conclusion is then G must contain a cycle. All right. Okay, so let's start with the proof here, right? So we're gonna, again here, these are our assumptions. So by assumption, G is connected. Okay. And then, so from there, let's say we have G being a connected graph, and by construction, we're gonna delete as many edges while still preserving connectedness. Okay, so we'll remove an edge as long as I still have a connected graph, right? Again, our theoretical graph here, right? Maybe I remove 1, maybe remove 10, maybe remove none, right? So depending on what G looks like, but I am able to at least try to attempt this. Right now, in doing that, H is still connected. Right, again, that's by construction, right? Okay, by the process that I described. All right, 2, now here this one is a little, we have to work to get our mind around this, right? H has no cycles. Right? Now, if it did, we could still remove edges, right? Think of, let's say here, like this, we can still remove this edge here. Right? And it's still connected. Right? And now we've eliminated the cycle. Notice here at this point, I can't remove any more edges, right? And still be connected. Right? So H has no cycles. Okay. So from here, what we have is that H is a connected graph. cycles. In other words, it is a tree. All right. So that means that the edges in H must be equal to V minus 1. All right, properties of trees. Now, H was obtained from G, so the edges in H must be less than or equal to the edges in G. All right, because again, maybe we removed some, maybe we didn't, right? It might have already been connected with no cycles, right? Remember, our only hypothesis is that it is connected. Okay, so by substitution here, we have V minus 1 must be less than E of G. All right. Now, in other words, E of G must be greater than or equal to V. All right. Okay. Okay, now if G had no cycles, G would be a tree. Because it is connected, right? That would mean that E of G would have to equal to V minus 1. Okay, and actually here going back, I think here, my apologies here, that's here. This is by assumption. All right, going back to our initial problem, V must be less than E of G plus 1. All right. Okay. All right. So we have E of G to be greater than V. Okay, so if G had no cycles, G would be a tree, which means E of G would be equal to V minus 1. But here we have a contradiction, right? G can be equal to V minus 1, but also greater than or equal to V. Right. So that means that G must contain a cycle.